Hi guys, good morning. You are welcome to my YouTube channel, the Explicit Stories, and my name is Dr. Joseph. In today's video, I shall be taking us a topic called Electronic Theory in Organic Chemistry in a course called Chem 113, Chapter 3 to be precise. Now, in this course or in this topic, I'm going to be teaching you how to fill electrons into their various orbitals without wasting much of your time or without stressing yourself at all. Before we get started, let us make a brief introduction to what the atom is. The first atomist in the 5th century was Democritus. Democritus was the first atomist in the 15th or in the 5th century, sorry. Now, after his postulation, two persons were actually against his theory, Plato and Aristotle. Now, Democritus said that the atom is, every matter is made up of atom, which is what highly indivisible, okay? Then after his postulates, as time went on, Ernest Rutherford actually said that no, that the atom can actually be split into its various components through what? Radioactivity, all right? Now, the atom can be split into electron, which is found revolving around the atom. Now, proton is actually a positively charged entity. The neutron is a neutral entity, while the electron is a negatively charged what? Particle. The nucleus is of course what? Positively charged. Now, in the chapter 1 of this course, I did teach us the various persons. Okay, please, that should be Chem 111 in organic chemistry. So I taught us the different personalities who were involved in bringing about the atom, everything about the atom. Okay, now the atom has, or every element has an orbital, and every element has what? A given shell. Now, the shell of an orbital has its maximum number of electron it can actually accommodate. Then every electron has an orbital. Now, every orbital has a maximum of electron that it can what? Accommodate. Let us get started. What is an orbital? An orbital is, I don't like this marker for now. Excuse me. What is an orbital? An orbital is a region of space where there's what? A high possibility of locating dash. An orbital is a region of space where there's a high possibility of locating dash. A, proton. B, electron. C, neutron. D, nucleus. The answer is what? Proton. The answer is proton. Don't try that. Even after the generation, don't teach your children that orbital is a region where there is a possibility of locating a proton. Don't try that. Even in your dream, try not to do it. Please, the answer is what? Electron. The orbital is a region of space where there is a high possibility of locating what? An electron. Okay? Take note of that. Okay? Every shell, we have major shells and we have subshells, otherwise called what? Orbitals. Now we have the K, L, M, and N shells. These are called what? Azimuthal. These are called principal quantum number. And principal quantum number is denoted as what? Small letter n. In principal quantum number, which is KLMN, we start ranging from 1, which means K is 1, 2, 3, 4. That is what? In principal quantum number. But the type of quantum number that now divides shells into orbitals is called what? Azimuthal quantum number. And they are S, P, D, F. Now, SPDF are sub-shells, otherwise called what? Orbitals, and they are what? Azimuthal, or momentum, or subsidiary or angular momentum quantum number. Please, SPD and F are azimuthal momentum subsidiary or angular momentum quantum number, which means if I don't call it azimuthal, I can call it momentum or subsidiary or angular momentum quantum number, and it is denoted as what? Small letter L. Okay, which means anything that has to do with orbital is to what? Azimuthal quantum number. Anything that has to do with shells is what? Principal quantum number. In azimuthal quantum number, we start reading from 0, 1, 2, 3, so on and so forth. So please take note of that. Now, why the type of quantum number that dictate how electrons should spin up or down, or just up or just down? It is what? The spin quantum number. Spin quantum number. And the spin quantum number possesses either -1/2 or +1/2. Please take note of that. We now have the last one called what? Magnetic quantum number. So these are the 4 types of what? Quantum number that we have. Do not forget the KLMN are what? Principal quantum number, and they start ranging from 1, while the SPDF, which are the subshells or the orbitals, are the azimuthal or momentum or subsidiary or angular momentum quantum number, the spin quantum number, and what? The magnetic quantum number. Good. Now, since we've established these facts, now a given element has a certain amount of orbital it can actually what? Possess. All right, it has a certain amount of what? Or a certain number. Let me use the word number, not amount now, please. A certain number of what? Orbital. Now, I told us that an orbital is a region of space where there's what? A high possibility of locating an electron, not proton, please. Now, if we were to enter electrons into a given orbital, certain rules are to be held to. Certain rules are to be obeyed. Now, these rules were discovered by my students. I taught them. They were my classmates. Oh, yes. Now, I taught them. They were my classmates. Now, these rules are, we have one, the Pauli's exclusive principle. The Pauli's exclusive principle states that no electrons in its atom will have all the 4 quantum numbers the same. Pauli's exclusive principle states that no 2 electrons that is in a given atom will have all the 4 quantum numbers the same. Never. Number 2, we have the Hund's rule. Now, the Hund's rule states that in entering electrons into their various orbitals, electrons should be entered singly first before we start to pair. This rule states that in feeding electrons into their various orbitals, electrons should be filled singly first before pairing. Okay, and number 3 is what? Alpha's rule. Alpha's rule. This rule states that in filling electrons into the degenerate orbitals, okay, orbitals belonging to the lowest, orbital belonging to what? Lower energy level should be filled first before orbital of higher energy level. This rule states that in filling electrons into the orbitals, orbitals of lower energy level should be filled before orbitals of higher energy level. That is to say, okay, let me illustrate that. Okay, before I go into that, I'm going to use an example to explain these rules. Okay, Now, let me quickly say this. To, to determine the number of electrons an orbital possesses, we make use of what? N squared. We make use of what? N squared. To determine the number of orbital found in a given shell, we make use of what? 2L plus what? 1. I told you guys that anything that has to do with orbital is restricted to what? Azimuthal quantum number, which is what? L. Now, I told us that S is what? 0. We start reading from what? 0. Which means that wherever I see L, I'll put what? 0. So I now have it to be 2 times 0 plus 1, and that is what? 2 times 0, 0 plus 1, 1. Which means that the S shell has what? 1 orbital. Now the P is equals what? 1. Which means that 2 times 1 plus 1, and this is what? 3. Now which means that the P shell has what? How many orbital? 3 orbital. Now I have D is what? 2, which means 2 times 1, 2 times 1, okay, no, 2 times 2, sorry, 2 times 2 plus 1, I have what? 5. That is what? 5 orbitals. Then F equals 3, which means that 2 times 3, 6 plus 1, 7. That is what? 7 orbital. That is how it is. If there are 3 orbitals here, how many electrons do you think we found in the orbitals? We have what? 6 electrons. We are going to be having what? 6 electrons. So take note of that. Take note of that. I think. Okay, now, fine. To know the number of electrons found in a given orbital, we are going to be using 2n plus 1. 2n plus what? 1. I don't know. Is that correct? Okay. Okay, no, we use n squared, okay? We use n squared. Since we've established this fact, all right, let me now use these rules to explain something. Now, let's take, for instance, our carbon. I think I'll stand this way. Carbon atom. Carbon atom has atomic number what? 6. Carbon has atomic number 6, which is what? 2, 4. A valency greater than 2, but a maximum of what? 4. Let us do it. I have one orbital, which is 1s, 2s. I believe we know this already. Then the P, I told you it has how many orbitals? 3 orbitals. Now, which means that we have we are going to be having what? 10 electrons normally. But since we have 6 electrons, we are going to be obeying Hund's rule first, which states that if we are entering electrons into these orbitals, we have to enter each of them singly before we start to work pair, which means I'll put one like this, put one like this, put one like this, put one like this, and put one like this. Now I've entered all the orbitals singly, but we still have 1 electron left. We have 6, but we have 5, so I'll put it here. So this becomes 1, this, don't forget, this 2p, all right? Now this is what? The excited states of what? Carbon. Now this excited state is to what? Hund's rule. Now let me now use Albert's rule. Albert's rule states that filling electrons into their orbitals, electrons, that is orbitals of lower energy, which are the x's, should be filled first before orbitals of what? Higher energy level. This same carbon atom, I have S, that I have to enter these x's first before the p, all right, which means I'll say 1 up, the other one down, 1 up, the other one down, 1 up, okay, 1 2 3 4 5 6, all right. So So which means that we now have this is what the ground states, the ground state of what carbon. Since we have one empty what shell, which means that the ground state is what Albers rule. Now from these excited states, okay, let me use this one again. Let me use this one. If we must obey Ohm's rule based on the excitation of what carbon atom, now we'll, like just at the first time we did 1, 2, 3, 4, 5. I have what 6. Am I correct? Oh, 1, 2, 3, 4, 5, 6. Good. Now, which means that I have 1s, 1s, 2p. Now, normally this do okay. Look at it here. I should be specific. This was what we had initially. We were having what one empty orbital. Now we are taking one electron from this s. We'll put it here. We now have only one electron here. Now I can now say this one is 2px, 2py, and 2pz. Therefore, I can now say 1x2 because there are 2 electrons, then 1s1, then 2px1 because there's 1 electron, then 2py, okay, yes, y1, then 2pz1. So this is the excited state of carbon, which means that the ground state is to Albers rule, and the excited state is to what Ohm's rule. So please take note of that. It is very, very important. Now, please take note of this. Which of these is not a degenerate orbital? Which of these is not a degenerate orbital? A, S, B, P, C, D, E, F. Which of these is not a degenerate orbital? The answer is, hope is recording. Yes, thank God. Please, the answer is what? S. S is not what? A degenerate orbital. I'm not trying to, that is the answer. Eh? P, D, and F are what? Degenerate orbitals. They are orbitals of higher energy level, while S is an orbital of what? Lower energy level. Okay, since we've established that fact, now energy of lower orbital. Energy of lower orbital is called what? Bonding energy. The father. We all must be intelligent. Now, the energy of lower orbital is called what? Bonding energy. But the energy of higher orbital is called what? Anti-bonding energy. All right, please. The energy of lower orbital is called bonding, while the one of higher energy orbital is called what? Anti-bonding energy. Please, the mixing of 2 or more orbitals result in molecular orbital. The mixing of 2 or more atomic orbitals result in what is called what? Molecular orbital. Please, hybridization is a mixing of 2 or more orbitals to produce what? Hybrid. To produce a hybrid. Oh God. To produce a hybrid orbital. You know, hybridization is one of the terms used in genetics. Alright. So the crossing of 2 different parents to produce a much more adaptive orbital. To produce a much more adaptive organism called what? Hybrid vigor. Hybrid vigor is genetics, but hybrid orbital is called what? Hybrid orbital is the word hybridization in what? Chemistry. Hybrid vigor is the word biology. So the mixing of 2 or more orbitals it's called hybridization to produce a beta orbital called what? Hybrid orbital. Take note of that. Now, so that is for that. We now have different, we have the sigma bond and we have the pi bond. Okay, before I go into that, I'll give us the shape of orbitals. Now the S is what? Spherical in shape. The S is what? Spherical in shape. Like this. Alright, it's spherical in shape. The p orbital is what? P orbital is what? Dumbbell. The p orbital is what? Dumbbell. Now the d orbital is what? Pi dumbbell. Which means that the combination of two p orbital give what? D orbital. Look at pp, and that becomes what? By dumbbell. By dumbbell. Then the f orbital is what? Complex in form. It is complex in form. Now, how do we form? We have the sigma bond, which has this sign. Let me just use. We have this sigma bond, and we have what? Pi bond. Pi bond. Now, how are these bonds formed? Now, the linear combination of s orbital, the linear combination of s, this s is s, linear, it will produce what? Sigma bond. Sigma bond. Sigma, the combination of two linear s orbital produce what? Sigma what? Bond. Now the combination of two linear pi orbitals, like if I have one like this, oh good, how am I going to draw this now? Good. It's too big. The linear combination of two pi orbital produce what? Sigma bond. Linear combination of two pi orbital, two pi as p orbital produce what? Sigma bond. Then the combination of one s orbital and one p orbital, the combination of one p orbital and s orbital will produce what? Sigma bond. Take note of these things. The linear combination of two x orbital produce sigma, two pi orbital produce sigma, s and pi produce what? Sigma. But the hope is recording. But the lateral combination of two pi orbital will produce what? A pi bond. I know you have been waiting for pi bond. No one can form the pi bond, and we have eventually formed it. If I have to like this, because I'm something like Christmas goods. Because if I have like this one pi, this one p orbital, like the lateral combination of two parallel, orbital. Jesus, this diagram has epilepsy. Jesus. So this part here is what? Pi bond. So, which means that the lateral combination of two parallel p orbitals will produce what? A pi bond. Please, pi bond is weaker than sigma bond. It therefore means that sigma bond is much more stronger than what? Pi bond. Okay, now I've told you how sigma bond and pi bond is or are formed. Now let us now look at shape of elements or compounds. Shape of elements or what? Compounds. Please, CH4, NH4, these two guys are what? Tetrahedral. They are tetrahedral in shape, and they have a bond angle of what? 109.5 what degree. Any compound you are having four outside, this is the central atom and this is the central atom, you have what? A tetrahedral structure, which means that the carbon atom in this methane, the carbon atom in methane is what? Tetrahedral in shape, and it was has 109.5 degree as what? The bond angle. Please, it is what? sp3 hybridized. sp3 what? Hybridized. Then certain diatomic elements like chlorine, nitrogen, hydrogen, or fluorine, bromine, iodine, like diatomic elements, they are all linear. They are all linear in shape, and they have a bond angle of what? 180 degree. Take note of that. Which all alkanes are sp3 hybridized. Alkanes are sp3 what? Hybridized. Then alkenes are sp2 hybridized. So if I have sulfur hexafluoride, that is sulfur hexafluoride, this guy is what? Octahedral. It's octahedral in shape. It's octahedral in shape. Now, if I have phosphorus pentachloride is triplanar by pyra Okay, so I said phosphorus pentachloride, which is triplanar bipyramidal in shape, and it has a bond angle that is between 90 degree and what? 120 or 180 degree. Now you check, you confirm that. Okay. Now, because some textbook will write 90 and 120, 90 and what? 180. Okay. Exactly. We now have certain elements that are what? Planar. All right. That is planar element or compound. We have NH3. NH3 trigonal planar in shape, and it has a bond angle of what? 120 degree. It is sp2 hybridized. It is sp2 hybridized. Okay. So other compounds such as beryllium chloride, carbon 4 oxide, nitrogen 4 oxide, they are all what? Linear in shape, and they have a bond angle of what? 180 degree. So at this point, we'll call it a day. If you just don't understand some parts which I've treated so far, just drop it on the comment section and I shall attend to you with immediate effect. Now, take note of shapes of molecules. Please, water, good. Water is V-shaped, angular, or bent. Don't ask me how. No, not your trying. Now me discover now. Do not ask me why is it V shape or why is it angular or bent? No, no, don't ask me. Go and ask the person that said it. I don't know. I cannot answer that kind of question because I know that is what you're asking yourself. So at this point, we'll call it a day. Do have a wonderful day. Then in our next part, we are going to be treating the part 2 of this chapter 3. As I'm rounding off this topic, I'm also using questions to round off the topic as well. So thanks for watching, and please endeavor to subscribe.